The new variation with time is plotted in red. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage psi. In equation form, we get EMF is proportional to rate of change of magnetic flux. Okay, let's take a look from the side view, where the eye is looking from left to right. The delocalized electrons in the aluminum will oscillate together with the aluminum sheet. Okay, the magnetic field points out the page. So when the aluminum is moving downwards by Fleming's left-hand rule, these electrons will experience a force to the right. The resultant motion is downwards and rightwards. The horizontal component of the velocity will in turn experience an upward force based on Fleming's left-hand rule. This upward force dampens the oscillations of the aluminum sheet. The same thing happens when the aluminum oscillates upwards. Okay, alternative explanation. When the switch is closed, a current flows through the electromagnet, causing it to generate a magnetic field. As the aluminum sheet oscillates, the delocalized electrons move relative to the magnetic field and experience a magnetic force. The motion of the electrons is an effective electric current, and the direction of the magnetic force is given by Fleming's left-hand rule. This magnetic force causes the electron to move, producing an induced current. This kind of current is known as eddy currents. The flow of the eddy currents produces a magnetic field. By Lenz's law, the eddy currents will flow in such a way to oppose a change in magnetic flux. The magnetic field produced by the eddy current interacts with the external magnetic field, causing the oscillations to be damped. Note that in terms of energy considerations, the induced eddy currents causes Joule heating in the aluminum plate. This dissipates the energy of the system. Connect a variable resistor in series with the electromagnet to vary the current and hence the magnetic flux generated by the electromagnet. Start with the largest possible resistance. A larger magnetic flux generated will cause larger induced currents when the aluminum sheet is set into the initial same amplitude of oscillation. Displaced for equilibrium by a same displacement can be measured using a meter rule. This causes a greater Joule heating and faster dissipation of the energy of the oscillatory system, and hence damping can be increased. The current in the electromagnet can be changed by adjusting the variable resistor till the system returns to equilibrium without oscillating. The time taken for it to return to equilibrium can be measured with a stopwatch. Critical damping is demonstrated when the aluminum sheet returns to its equilibrium position after being displaced in the shortest time without oscillating.